Our next speaker is Professor Anirban Sengupta, Professor of CSC, Indian Institute of Technology, Indore, MP. He will be talking on high-level synthesis-based hardware security and IP core protection. So first, I will request Sri Dilip Burman, Deputy Controller, Office of CCA, to felicitate our speaker. Professor Anirban is a senior member IEEE. He received the PhD degree in Electrical and Computer Engineering from Ryerson University, Toronto, Canada. He is a professor in Computer Science and Engineering at the Indian Institute of Technology, Indore, India. He is an elected fellow of IET, a fellow of British Computer Society, and a fellow of IETE. He is also an IEEE Distinguished Visitor of IEEE Computer Society and an IEEE Distinguished Lecturer of IEEE Consumer Technology Society.
Special thanks to Dr. Mohan and Dr. Balaji for inviting me for this talk. It's a privilege to be part of this excellent platform and conference. The title of my talk is Hardware IP Security and Trust. It's an emerging area of research and it involves a lot of cryptographic applications as part of that. So for beginners, what is hardware security? So it's basically an emerging area of research that basically focuses on two main branches of securing hardware IPs, which are widely used in different sort of applications in consumer electronics, as well as in various computing domains, in machine learning, in medical systems, and so on. The two most important branches of that comprises of authentication-based techniques and obfuscation-based techniques. So obfuscation-based techniques can again be further subdivided into something known as structural obfuscation and functional obfuscation. In structural obfuscation, what is typically done is the hardware of the respective computing device, which could be in the form of an application-specific processor or a general-purpose processor, that is structurally obscured in such a way that it becomes harder for an attacker to interpret and deduce. On the other hand, the functional obfuscation basically aims to provide an active mode of protection and in a way kind of encrypt the gate level circuit of the IP design. Now let's take an example of a typical camera. So if you see that it uses CCD and it converts an analog image into its digital counterpart. But that's just not enough because it also uses a lot of data calculations in the form of JPEG, compression and decompression, as well as a lot of image processing engine, as you can see in the lower half of the diagram. So the essence here is to protect this IP or hardware designs against external threats like IP piracy, false claim of IP ownership, reverse engineering, Trojan attacks, and so on. This is a typical example of a complex JPEG codec. And this has been done, designed in our lab at IIT. And this typically kind of indicates the complexity of the JPEG codec application when it is designed at the RTL or at the gate level, abstraction layer. There could be similar applications like finite impulse response filter, convolution filter, which is an important application in machine learning, and an image processing, DCT, TFT, and so on, as well as there are other sort of image processing applications like image blurring, image sharpening, and so on. These are some of the very highly popular applications which needs security and protection against standard cyber attacks. Well, let me talk a little bit about the different sort of attacks that have been explored in the scientific literature by the scientific community so far. And the work on hardware security has been going on in the last 15 years or so. It's still a young, area of research compared to the other, domains. Now, as you can see from here, we basically have the first one, which is false claim of IP ownership, which talks about how you can protect the ownership of your IP and nullify the false claim of IP ownership. The other things that includes are, piracy claim, which may have further classifications in the form of counterfeiting and cloning, as well as other things like Trojan insertion. Now, these Trojan insertions are backdoor malicious entry during the IC design supply chain, and they can be done at different levels of abstraction starting from, architectural synthesis to RTL, gate, layout, and so on. In the typical SOC life cycle, as you can see here, it starts with the IP vendor, and then it moves with the SOC design house, followed by the foundry where the fabrication takes place, and finally the deployment. Each of these stages are vulnerable and susceptible to different hardware threats. So, for example, the IP vendor house could be responsible for inserting hardware trojans. Okay, and it can have different sort of payloads. For example, it can have battery exhaustion attacks. It can have performance degradation payload. It can have things like hampering the energy of the final IC and so on. So it could be a lot of different payloads. And in the SOC design house, one of the most important threats is IP piracy. Now, this basically means that instead of the actual IP, a pirated version of that is infused in the design chain without the knowledge of the actual IP vendor. At the foundry stage, it's again considered untrustworthy. So there could be issues like implantation of Trojans, overproduction, cloning. And finally, at the deployment stage, there could be things like leakage of secret information, reverse engineering, and so on. So these are some of the widely accessed, CAD-based security tools, which are publicly available for different researchers. And they mostly, exploit things like compiler transformation and structural obfuscation for protecting DSP circuits. Things like, structural obfuscation augmented with IP locking techniques can also be used. Sometimes things like, locking blocks along with encryption blocks like AES, SHA, and any other lightweight solutions could be integrated in order to guard against removal attacks and things like, SAT attacks and so on. So all of these have been integrated into some of the publicly available tools which are available, and some of them have been developed by us at IIT Indore. The interesting part here is that traditionally people have been doing it mostly at the RTL or gate level. However, if you raise the abstraction level and you move into the architectural level phase of the IP or computing hardware design, which in many communities are often used as application specific processors, high level synthesis becomes a very crucial framework. What happens in high level synthesis is that you start with the design space exploration, which finds out your optimized architecture for your computer hardware, followed by scheduling, hardware register allocation, and binding. And then you move on to other things like interconnect designing, controller design, data path, to finally build the IP at the RTL, which can be further synthesized using commercial CAD synthesis tools from Intel and AMD to bring it at the gate level. Now, in these in synthesis process, the hardware security framework can be augmented, okay, in the form of something known as watermarking or something known as obfuscation or something known as logic locking. So I'll touch upon one of it. So palm print biometric based hardware IPP is a very popular solution where from the palm print of the IP vendor house, it could actually generate a lot of secret information which can be used as a digital evidence with multiple security layers. And finally, that can be converted into palm print based watermark, which could be implanted into the IP design secretly as an imperceptible, invisible watermark, which could later be used in order to prove the false claim of IP ownership. And it can also guard against IP piracy. So essence of it is that it basically acts as a deterrent for an attacker, okay, before any sort of cloning or counterfeiting can potentially take place. I will not go too much into the algorithm side of it because of lack of time, but the basic essence of that is that it captures the high quality image of the palm print and generates using certain algorithms the nodal points from where the dimensions of each features are captured, and then with the help of certain encoding rules, it could be implanted into the RTL design stage of the IP. So this figure basically shows the different sort of palm print features which have been exploited. So we have exploited 19 palm print features, which could be converted into something known as palm print signature. Okay, either you could implant the palm print signature as an encrypted version, or you could just do it directly. Okay, encryption will add another layer of security before it could be converted into its respective watermark constraints. Once these constraints are implanted, okay, then again it needs to be verified. But for verification, we need to make sure that we have the respective watermark constraints embedded with the help of certain algorithms. Okay, so we have typically encoding algorithms which are known as graph coloring algorithms, which are often used for implanting the watermark constraints in the form of storage variables, okay, which are responsible for storing the intermediate outputs as well as the final output of the scheduling graph. In terms of the security analysis, basically the two widely used parameters are probability of coincidence and tamper tolerance. So probability of coincidence basically tells you that what is the probability of an unsecured design having the palm print watermark by coincidence. So lesser is the probability, more robust or strong is the palm print watermark. And tamper tolerance basically tells you what is the ability of the design to tolerate the tampering attack as well as removal attack. This graph basically tells you the comparison of the probability of coincidence and tamper tolerance of the palm print watermark with other some of the recent standard techniques, and it shows that it has been able to achieve lot lesser PC and a much higher tamper tolerance, which tells you the robustness of the technique. In the process of doing this, another important thing is that the embedding cost or embedding overhead of the security algorithm should not be high. Okay, so once the palm print gets embedded into the IP design, we also need to compute the design cost over it. So that is usually done with the help of things like normalized latency of the IP design and normalized area. So lower is the design cost, better it is. On a similar scale, there's something known as hardware steganography or IP steganography that is also used in a similar way, okay, to act as a watermark or act as a deterrent for the attacker. But if we try to compare the two, we find out that watermark in some respect is stronger than steganography. The only problem with steganography is it does not start with the signature of the IP vendor directly. It extracts the signature from the design itself. Okay, so that's how the two techniques have some variation. Otherwise, in terms of design overhead, both are comparable. And in essence, hardware steganography is actually lower than watermarking in some cases. So this slide basically talks about the two variations of finite impulse response filter. One is a watermarked version, another one is a non-watermarked version. So optically, we cannot make out, which is watermarked and which is not. And that's the strength of the technique, that it is imperceptible and invisible by nature. However, for an IP vendor, he can easily decode and extract the information when he has to prove it in front of a third-party authenticator. In case of steganography, one of the other things that it could be used for is when you want to detect IC counterfeiting. So for example, you have a brand X IC and this brand X IC contains the stego mark, then it is probably not a counterfeit. Okay, if it does not have the hallmark of the respective firm, then it is probably a counterfeit version. Okay, so here basically that hallmark or steganography mark is acting as a seal of the actual authenticated IP vendor. On the contrary, if there's a brand Y and the brand Y contains the stego mark of brand X, then that means it's probably a copy of the original IP. And finally, we can also resolve the false claim of IP ownership in a forensic lab. Okay, when there are two cases, one is the attacker who is trying to claim the ownership of the IP and the original IP vendor is also there. So with the help of these stego constraints, okay, the original IP vendor can establish his or her identity and the integrity of the design in front of the third-party authenticator. This shows yet another design of something known as discrete cosine transformation, in short DCT. DCT is a very important application in JPEG codec, okay, and it's widely used in image processing, video processing and stuff. Now this shows the DCT before steganography and this shows the DCT after steganography. So as you can see, only the multiplexer input sharing changes as a result of secretly embedding the watermark into the IP design. Now, IP core protection has also been done using digital signature. So in this case, what typically is done, the IP watermark information is passed to a crypto hash function, which generates the hash, and then it's signed using RSA, okay, using a private key. And then finally, the digital signature of the respective IP vendor, okay, is generated, which can later then be again encoded using certain encoding algorithms and converted into its constraints, which could be embedded into the IP. There is another innovation in this area, which is known as triple phase watermarking. So triple phase watermarking basically tells you is that you could implant the secret digital evidence or your seal of the IP vendor at different phases of the HLS process. So for example, one of the phase could be scheduling, the second could be hardware allocation, and third could be register allocation. Now with this, it will have independent watermarks at different phases, which could be unified using certain concatenation rules to produce something known as triple phase watermark, which could again be implanted into the RTL description. The difference with digital signature and a normal watermark, if you do a contrasting study, is that in case of digital signature, it uses hashing and encryption. Okay, and in case of watermark, it uses known as variable encoding. It's encoding rules that is capable of generating the watermark. So that is basically the fundamental difference between the two techniques. So I'll move into the other branch of hardware security, which talks about obfuscation. Now, obfuscation, as I said, is a technique through which you can obscure your design and make it more harder, okay, resilient against reverse engineering. So what reverse engineering basically does is it tries to extract the netlist of the IP without the knowledge of the actual IP designer. So obfuscation makes it more harder and it thwarts reverse engineering to a large extent. So in the literature, compiler-driven transformations, which could directly be applied on the graph level designs of the IP in the form of things like redundant operation elimination, logic transformation, tree height transformation, and so on, could be performed in series to produce the obfuscated CDFG. Now, CDFG stands for control data flow graph of the respective design. And then again, it could be made resilient against transient faults and so on to finally make an obfuscated version of the IP. Similar sort of things can be done for image processing applications like blur filter, sharpening filter, vertical embossment, and so on. And as you can see from the results here, that in the entire process, the functional obfuscation or the structural obfuscation does not disturb the final functionality of the IP. That's the most important thing. In the process of embedding watermark or obfuscation, you cannot make any changes to the functionality. So it has to be zero tolerance for change of functionality as compared to other domains like image watermarking and so on. This is another example of an obfuscated design of a fault secured FIR. Now, fault secured FIRs, these are applications often used in space applications and in environments which has a lot of radiations, which involves alpha and neutron particles. So obfuscation of fault secured designs is also very popular, and they can also be obfuscated using the technique which I just now mentioned in my previous slide. As you can see, the difference between a non-obfuscated version, okay, is a lot of structural changes, but ultimately the final output or functional correctness will be same in both the cases. So the concluding slide would be that the future of the consumer electronic systems, IoT or CPS, okay, we are often surrounded by these consumer devices like camcorder, smartwatch, smartphone. The future lies in the area of energy security trade-off. So interested researchers can actually pursue doing research in this front. Thank you so much, and I'm open to questions.
Hello, Professor. My name is John. I am from a private company. This topic that you have been taking, right, the hardware security is phenomenal. I just have a generic thing, especially our nation being a great contributor towards the silicon industry, and now that we are growing in the silicon industry, I feel this is one gap where there is a challenge between the education and the industry that needs to be addressed. Because including my son who's doing his electronics engineering, when we go through the syllabus, we see them cybersecurity as part of networks paper, right? The basic thing.
Right.
But what you just showcased was something fantastic, right? They go to the gates level to address the backdoor entries, the puffs, and other things. I feel our Ministry of Electronics and Information Technology should take enough steps to address this at the education level. So
Absolutely.
that I completely agree that this is a research area, but still, since we are growing in the semiconductors where we are trying to fabricate and grow our chip designs,
Absolutely.
I think at the education level this needs to be addressed. I'm just trying to make this as a point.
I completely concur with you, and in fact, Ministry of Electronics and IT has taken some initiatives in this regard. I mean, they do a lot of funding for sponsored projects, but at the education level, I think obviously there are some gaps that are still pending. And unfortunately in India, the areas such as this are not that much taken up yet, but in US, DARPA, which is the government, security agency, they have huge investment on this front. DRDO needs to take this up in a more proactive manner, and I think it will probably come up in the next 5 years or so. Thank you for your feedback.
And also a kind request to CDAC, which is a premier institute, especially in terms of hardware testing, right? There's a side channel attack or fault injection attack. Always we have to be dependent on the West, right? Either we have to take all the way to US or to the Netherlands in order to get this tested, especially in the automotive and the IoT hardware testing.
Correct.
So if we can plan this for the future for our nation, it's
Absolutely,
going to be
absolutely. Totally agree, totally agree.
Hello, good afternoon. I'm Kavita here. I'm from PSU. I just wanted to know this, how to protect sensitive data in cloud computing and IoT devices.
Sorry, I didn't get your question.
How to protect sensitive data in cloud computing and IoT devices.
How to protect?
Sensitive data.
Okay, got it. So, if you're talking about data protection, I think, there are a lot of techniques, okay? Security as a service for cloud computing is, commercially deployed in several places. And for data protection and data security, there are a lot of, algorithms available, lot of commercial de facto standards available, okay, which could be used, like AES is one of the standard ones and several others. The most important thing which becomes very crucial now is how to actually handle if there is any sort of side channel attack on those data, okay. So the designs have to be therefore side channel resilient, and how to do that, of course you need to think about what are the side channel parameters that could potentially be used by or misused by an attacker in capturing or leaking the secret information or encryption key. So I think a lot of research has to be done in that area, and then side channel attack resilient designs could definitely be made. Any other questions, please? Yeah.
Here.
Yeah.
See, this is a little intriguing. The hardware IP itself has its resource constraints, maybe performance, area and all that, to do certain tasks. To check the authenticity of the IP, you have to load some more crypto, some of it quite heavyweight. If that goes into the hardware, the overall again it stretches it, no? So your thing measure all that, balance and all that, many of these approaches.
So basically these IPs that I've been talking about, they could be from various domains. So I can give you some examples. In the cardiac pacemaker, that is the one which is implanted into our heart. So implantable cardiac pacemaker contains several IPs. Just imagine the situation if those IPs are not pre-verified before integration into those cardiac pacemakers. what would be the situation of the patient. It could have catastrophic fatal consequences. And it has been proven in research that those IPs, before integration, they could be hacked, and to such an extent that it could be made malicious internally by secretly inserting Trojans into that. And they start behaving erratically, unreliably when it goes into operational time. So therefore, things like authenticity of those IPs before they are actually implanted into the system on chip of those medical systems or of any consumer devices, that becomes very, very important. So that is the essence of this, talk or goal of the research here.
I agree. Critical would have measured. You pay certain cost for the criticality. But non-critical, where bulk of it is, that one measures that also. All I wanted to know was you measure the performance with and without that and so on.
Right. Absolutely. That is true. That is true.
Thank you for this very interesting talk, particularly the example you gave, one of those encoding with biometric, that's hand palm related one. I know it's not very related to your talk, I'm just asking the question, especially the creative work which is happening, it may be through artists or maybe video or images art. Do you know any similar encoding which is happening? So because of the AI now, all of them can be challenged. Anything which is happening so that the creative work of an artist can be still retained when we decode it, probably it may be helpful for our cyber security too. I know it's not directly related to your question, talk, but I thought I would just check.
Are you talking about multimedia objects like images and videos?
Yes, yeah.
So I think for multimedia objects, image watermarking and image encryption has been widely used. And one of the good things about that is that it could tolerate some sort of, errors in terms of the information. The non-critical part of the region of interest could still be, compromised to some extent, and that will still be good enough to prove the identity of the actual multimedia object. But in case of circuits, like hardware circuits, the biggest problem is it has zero tolerance for functional change. And that is the biggest challenge for designers here. Thank you. I'm unable to hear actually.
We were talking about security techniques, about this obscuring. So how about the masking? Is it one and the same like obscuring?
Masking? You're talking masking?
Yeah.
So masking is a pretty similar concept as obfuscation, basically. So when I say obfuscation, we are actually masking the structure and functionality of the design. So yeah, obfuscation is more technically correct when we talk about circuits here, basically. Any further questions from the audience? Okay. Thank you so much.
I will request Dr. Balaji, Scientist F, CTech Bangalore, to present a memento to our speaker.